Hey, welcome. Today, we're diving into the absolutely incredible electrical story that's playing out inside your chest right now, every single second. We're talking about the symphony of the human heartbeat and the amazing science that keeps it perfectly in rhythm. So let's just start with this question. Have you ever really thought about it? What is it that's actually telling your heart to beat? We're talking over 100,000 times a day. It's not just a muscle squeezing. It's this incredibly sophisticated electrical system firing with unbelievable precision again and again and again. And believe it or not, that entire story, from the beginning of one beat to the start of the next, can be broken down into 5 distinct electrical phases. You can almost think of them like 5 movements in a symphony, all happening inside a single tiny heart cell. All right, let's get into the nitty-gritty. Because to understand how we can possibly fix a rhythm that's gone haywire, we first have to understand what a perfect rhythm even looks like. We're about to listen to the individual notes that make up the heart's song. So, we're going to walk through these 5 phases, step by step. From the moment the heart cell is just waiting for a signal, to the massive spark that makes it contract, and all the way through to the final reset. It is truly a delicate electrical dance. Now, before we really get into that dance, let's get our key term straight: action potential. It sounds complicated, but it's really just the scientific name for that electrical signal we're talking about. Think of it like a tiny, super fast electrical pulse that flips a switch inside a cell, telling it, hey, it's time to do your job, or in this case, it's time to beat. Everything begins right here at phase 4. The cell is just, well, it's resting. It's sitting there with a negative charge, about minus 90 millivolts. It's calm, but it's also primed. It's like a coiled spring, just loaded with potential energy, waiting for its cue. And bam, there's the cue. Phase 0 is the spark. It's the downbeat of the drum. A signal arrives, and these tiny little gates called sodium channels fly open. In rushes a flood of positively charged sodium ions. This instantly flips the cell's charge from negative all the way to positive, a huge electrical spike. This is what we call depolarization, and it is the heartbeat. Okay, next up is something really unique and super important: the plateau. See, the cell doesn't just fire and immediately reset. It actually holds that positive charge for a moment. And it does this through a clever balancing act. As positive potassium ions start to leave, positive calcium ions come in. It keeps things stable. And why does this matter? This plateau is absolutely critical. It's what gives the heart muscle enough time to contract fully and powerfully push blood exactly where it needs to go. And finally, we have phase 3, the big reset. The calcium gates close, but the potassium gates stay open, so positive ions keep leaving the cell. This causes the charge to plummet all the way back down to its negative resting state. This whole process is called repolarization. It's literally repolarizing the cell, getting it ready for the very next spark. So here it is, a quick cheat sheet for our little electrical dance. You can see really clearly how each phase is dominated by a different key player. Potassium is in charge when the cell is at rest. Sodium is the star of the show for that rapid spark. Calcium takes over for the plateau, and then potassium comes back to handle the reset. It's just a beautifully choreographed exchange of ions. But what happens when the music goes off key? What happens when the conductor loses control and this perfectly timed sequence gets all jumbled up? Well, that's when we run into the problem of arrhythmia. To put it simply, an arrhythmia is a glitch in the system. It's what happens when any part of this 5-phase electrical story we just learned goes wrong. The beat can suddenly become way too fast, way too slow, or just completely chaotic and irregular. So how do we fix it? How do we get that orchestra playing in time again? Well, this brings us to the 4 main classes of antiarrhythmic drugs. Each one is cleverly designed to step in and correct a very specific part of that choreography. So when you're trying to fix a broken rhythm, the key thing to know is that there isn't just one magic bullet. Instead, doctors have a toolkit with 4 completely different strategies, and each one is designed to intervene in that electrical dance at a very precise moment. This table really lays out the whole game plan. Just look at how each class targets a specific part of the cycle we just learned. Class 1 drugs go after the sodium spark. Class 4 drugs target the calcium plateau. Class 3 drugs slow down the potassium reset. And Class 2 drugs, they work all the way back on the resting phase. It's all about precise, targeted intervention. So let's start with Class 1. They're sodium channel blockers. What they do is they intentionally slow down the spark, that initial massive rush of sodium. So if a heart is beating way too fast, too frantically, this is like telling the drummer to just chill out a little bit. Then you've got class 2 drugs, the beta blockers. They take a different approach. They work back on phase 4, the resting state, and they basically make the heart cells less sensitive to stress signals, which helps keep a racing heart in check. Okay, now for class 3. These are potassium channel blockers. They target the reset phase and deliberately make it take longer. By stretching out that reset process, they lengthen the entire heartbeat, giving the heart more time to rest before the next one fires. This can be crucial for stopping chaotic rapid-fire signals. And finally, class 4. These are calcium channel blockers. They go right after phase 2, the plateau. By limiting how much calcium gets into the cell, they can slow the heart rate and even reduce the force of the contraction. But here's the thing. Intervening in something as fundamental and delicate as the heartbeat, well, that's a serious business. These drugs are incredibly powerful, and with that power comes some pretty significant risks and trade-offs. Let's just take one common example, a class 3 drug called amiodarone. It has a half-life of several weeks. Now think about what that means. If you take one dose today, half of it is still floating around in your body weeks from now. And because it builds up so slowly, it can literally take months before you even see its full effect. This is not a quick fix. And because it sticks around for so long and affects so many different systems, amiodarone is a real double-edged sword. It can cause a whole host of really serious side effects. We're talking scarring in the lungs, liver damage, and it can even turn a person's skin a kind of blue-gray color. It really just highlights what a delicate balancing act treating arrhythmias is. And this isn't just about amiodarone. Other drugs carry their own serious risks. Some can cause a lupus-like syndrome. But here's the real paradox. Many of these drugs can cause something called QT prolongation. All that means is they make the reset phase of the heartbeat too long. And if that window gets stretched out too far, it can actually trigger a brand new and sometimes even more dangerous arrhythmia. It's a huge risk. We've been way down in the weeds, talking about ions and channels inside a single cell. So you've got to be wondering, how on earth does any of this connect to what a doctor actually sees in a clinic? Well, the answer is the electrocardiogram, or as we all know it, the ECG. And this is the big aha moment where it all clicks into place. Every single one of those electrical events we just talked about happening inside one microscopic cell gets magnified across millions of cells at once. And the combined result is that familiar waveform we see on an ECG. That massive phase 0 spark, that creates the big QRS spike. The phase 2 plateau corresponds directly to the ST segment. And the phase 3 reset, that creates the T wave. The ECG is a direct window into the heart's electric symphony. So this is where we'll leave it. The rhythm of our heart is this constant, incredible balancing act. On one side, you have this precise, natural, beautiful electrical dance. And on the other, you have these powerful chemical interventions designed to fix it, but that also carry their own risks. It's just a profound reminder of how complex and how beautifully fragile our own biology really is. Thanks for joining me for this explainer.